Okay, the last thing I want to talk about in this particular investigation is the concept of stability. And when talking about stability, there's actually two types of sections of the atmosphere that I need to talk about. And they're called CAPE and CIN. So in this investigation, we've been talking a lot about what happens as air rises. We talked about this parcel of air, how it's isolated from its surroundings, how it cools adiabatically. But the one thing I really haven't mentioned yet is that because of all of that, the temperature of the atmosphere and the temperature of this parcel are oftentimes different from one another. That being said, the difference is what determines if the air can rise or sink. If the temperature of the parcel is less than the temperature of the surrounding atmosphere, the parcel will sink. On the other hand, if the temperature is warmer in the parcel than the surrounding atmosphere, the parcel will rise. Now, how can we figure this out looking on a Stove diagram? Well, most plots that are automatically generated actually include the temperature of a parcel of air. Starting with the surface temperature, determining if the temperature or if the parcel is moist or not. You rise the parcel up in the atmosphere. Eventually it becomes saturated. And then you switch over to the moist lapse rate. And what we do is we compare this red parcel line to the right air temperature of the atmosphere line. And whenever the parcel is cooler than the atmosphere, like it is right over here, the parcel line, this red parcel line, is to the left of the temperature line. This is called CIN, or convective inhibition. So let me pull out a little arrow right here. This is called convective inhibition. This whole area right here is an area where the parcel is cooler than the surrounding atmosphere. So it can't rise in that case. Now, something can cause it to rise, something can force it to rise, but it can't rise on its own. Now, on the other hand, once the parcel gets up to here, sorry, let me get my cursor to show. A lot of times this cursor likes to disappear on me. Yeah, it's disappeared on me. Okay. That's okay. So once you actually get to a height of approximately 700 millibars, everything above that, up until almost 200 millibars, the parcel is actually warmer than the surrounding atmosphere. This is what is called CAPE, convective available potential energy. In this case, if you take the parcel and you push it up, and it makes it to this height, it is able to rise on its own. And as it's rising, it's expanding, cooling, condensing. It's creating clouds. And if you actually take a look, this layer of CAPE, which starts at about 700 millibars, that's 3,000 meters, and goes all the way up to about 200 millibars, or about 12,000 meters, that's approximately 9,000 meters that this air is able to just rise on its own. 9,000 meters, that's about 27,000 feet. So these clouds that are growing here can become very tall and oftentimes end up creating thunderstorms and maybe even tornadoes if the wind in the upper atmosphere is conducive to it. So again, CIN is whenever the parcel, and that's this red line here, is cooler than the surrounding atmosphere. That's the black line, the one that you drew in a few investigations ago. And then CAPE is whenever the parcel is warmer than the surrounding atmosphere. And in the case of CAPE, the parcel is able to rise. In the case of CIN, the parcel would sink. And it's these two things that greatly determine the stability of the atmosphere. If there's a lot of CAPE, that means there's a lot of instability. And that's a day that you can expect stormy weather. On the other hand, if there is no CAPE, and there's only CIN, that's a day where you're not going to expect any stormy weather, and instead, it's going to be very, very calm. And one of the biggest setups for severe weather is one just like what you're seeing here. You have a small layer of CIN near the bottom, which is keeping all of the air kind of down there. And as soon as some kind of mechanism, usually convection, forces that air to rise, as soon as it gets up to that level where it enters CAPE, it then just rises on its own.